Hello. In this video, I will talk through quantum computing and how the cybersecurity industry can leverage it to achieve a substantial advantage. Quantum computing is developing rapidly and gained plenty of traction in the rapidly evolving technology space. Many organizations already started to adapt practices that will help them use quantum computing for their own benefit. In this video, I'm about to give you a few examples how the Classiq platform can be used to implement real applications from the cybersecurity domain. Classiq, headquartered in Tel Aviv, Israel, developed a software that is designed to generate quantum circuits and optimize them, receiving a high-level mathematical model as an input. This approach saves the need to develop low-level gate design and provide even those without solid quantum background to develop advanced quantum applications. Let's talk about Shor's algorithm. Shor's algorithm intends to efficiently factor large composite numbers into their prime factors. This algorithm provides, arguable, the most prominent evidence for an exponential advantage of quantum computers over classical computing. Most implementations that exist today in the market won't always consider the modular exponentiation in a scalable way. The implementation that Classiq introduces today considers it profoundly and guarantees that the implementation will maintain its scalability also with larger quantum circuits, so the increase in the depth and width of a larger circuit will not be exponential. This implementation was done in our platform's very own programming language, QMod, using basic quantum gates and with relatively few lines of code. We start by picking a random number a which is smaller than the number n we want to factor. The algorithm checks whether a and n are co-prime. If not, then their common factor can be easily found on a classical computer, and we are done. If they are co-prime, we proceed with the quantum part, which calculates function f. F represents a in the power of x modulo n. This is the prototype of how the quantum circuit should look like, while the multiplication is shown below. In this demonstration, you can see how the quantum circuit looks at the Classiq platform. We can see the implementation of the Fourier transform to do the calculation below. This is part of a technique called quantum phase estimation, which we implemented at Classiq. Classiq have implemented more use cases that can be applied to various cybersecurity applications. Patch management is a common pain point for any large-scaled enterprises or widely distributed systems such as smartphones or IoT devices. Lack of appropriate patching was indicated as being a substantial cause for some high-profile cybersecurity breaches. Before we start, let's define some terminology. An organization wants to keep its assets, such as data or personal documents of employees or customers. The patch management problem is defined by how to prioritize the safest sequence of patch installations, given limited resources and time, in the most efficient way. Classiq's solution would be to dissociate the attacker's ability to move in the network by finding a MVC of vulnerabilities to path in the attack graph. The vulnerability graph, G, is a bipartite graph where open partition of vertices represents a network of assets and the other represents vulnerabilities. This is an example of what we would expect an attack graph of a complex network to be, where we can clearly see all the assets and the vulnerabilities. A kill chain, or an attack path, will look like that, where we can see the chain that leads to each asset. The vulnerability graph is transformed to a dual graph. We want to find the minimum set of vulnerabilities that cover this graph and patch them. This is an NP-hard problem that potentially can be solved on a quantum computer. When we have the dual graph available, we can solve the minimum vertex cover on it. First, we will build a model, seamlessly incorporates the graph problem using the QMod language. This is going to be solved using the QAOA algorithm. We can add parameters and constraints that the synthesis engine will consider when generating the circuit. Second, we will click a button to generate the quantum circuit. Classiq's visualization tool will enable us to optimize and analyze the quantum circuit. Lastly, we will execute the circuit on a real quantum hardware. We can choose the vendor and the specific quantum simulator or quantum computer. Let's run it with IBM's AER simulator. Within a few seconds, we will get the result of the execution. The energy, the time, and the energy convergence graph are being delivered. In the graph, you can see that as the number of iterations increases, the energy is getting to its lowest. These are only two of the Classiq implementation's quantum applications relevant for cybersecurity. Fill in your details and contact Classiq for more information on how to use quantum computers to better protect your business in the future.